Yes, we live again. My name is Adeyemi Abiodun. I'm the lead tutor at 300 plus academy.com. So, what we'll be looking at today is still on GCE 2023 Alternative to Practical. And the experiment we have for you today, which, like I always say, is a probable question. Take it seriously, is on electricity. It is about a circuit diagram showing a capacitor connected in series with an ammeter. Yes, as you soon see displaying on your screen, you're going to see two figures talking about a voltmeter and an ammeter. Okay, in the very first question here, we were told to record the values for I, which is the current on the ammeter, and corresponding values V for the potential difference on the voltmeter, talking about the voltage. So what you're going to see here, you're going to see two figures, um, figure 3A and figure 3B. For figure 3A, you want to read the voltage reading, and for figure 3B, you want to read the current, that's the ammeter reading. Okay, we have this experiment performed for six values, performed 6 times, so that we get accurate result. So what you have written on the board already, as you see on the figure 3A and figure 3B, taking off with the ammeter reading. First we have 0.10 for the first reading, 0.20 for the second reading, 0.30 for the third reading, 0.40 for the fourth reading, 0.50 for the fifth reading, and 0.60 for the sixth reading. That looks pretty, you know, coherent, because you're looking at a difference of 0.10 amperes all through. So for the voltage reading, we have 0.20 volts for the first reading, as you see displaying on your screen. If you look at the graduation very well, you would see that the first reading for the voltage is 0.20, the second is 0.40, the third 0.60, the fourth 0.80, the fifth 1, the sixth 1.20, looking at the difference of 0.20 volts in the reading from serial number 1 to 6. Okay, on question Roman figure 2, we were told to evaluate I raised to power minus 1. That's the inverse of the current, and that's what you have here. My current raised to power minus 1, which means 1 over I. That means my unit is no longer going to be in amperes, but it's going to now be in ampere raised to power minus 1. That's per ampere. So if I deal with 1 divided by 0.10, 1 over I, the first reading is 10. 1 divided by 0.20, that's 5. 1 divided by 0.30, 3.333. That's why I'm putting this to 3 decimal places. 1 divided by 0.40, I am getting 2.5. 1 divided by 0.5, I am getting 2. And 1 divided by 0.6, I am getting 1.667 approximated per amperes. That's for expressing inverse of my current, because that's the instruction we were told in question Roman figure 2. I was also told to evaluate the inverse of the potential difference of the voltage. So my voltage is 0.2 for the first reading. 1 divided by 0.2, I'm going to get 5. That's going to be in per volt. That's volt raised to power minus 1. 1 divided by 0.40, I'm going to have 2.5. 1 divided by 0.60, 1.667. 1 divided by 0.80, 1.250. 1 divided by 1, of course, 1. 1 divided by 120, 1.20, 0.33 per volt. So I've been able to answer Roman figure 1 and Roman figure 2. For Roman figure 3, we were told to tabulate our readings. I have tabulated that already. Then for Roman figure 4, we were told plot a graph of the inverse of the volt. For Roman figure 4, we were told plot a graph of per volt, volt raised to power minus 1 against inverse of the current, that's in per amperes. So that means that this is going to be on the vertical axis and this will be on the horizontal axis. So quickly we're going to get into the graph. So the first thing I do when I want to plot my graph is to write my title telling exactly what the examiner wants. So here I'm going to be saying graph, okay, graph of the inverse of the voltage in per volts against inverse of the current in per ampere. So that is the title. Once I've done that, the next thing I want to do is to draw a straight line, not broken lines, for my vertical axis irrespective of the figures I want to put there, and also get one down for my horizontal axis. Recall you need your 30 cm ruler for you to be able to plot on paper, but here I have my own ruler. So okay, let me make the line a bit more brighter and thick so that we can have a very good plot. So regardless of what figures you're going to be putting in, the first thing is for you to get down your horizontal and your vertical line. And like I do say, it's a lot more easier plotting on paper as against plotting on a whiteboard. Okay, I'm going to start both from the zero origin. Okay, so it means that this vertical axis talks about my voltage, inverse of my voltage in per volts, and the horizontal axis talks about the inverse of my current, that's per ampere. So if you look at the question displaying on your screen, say plot the graph. Okay, so the next thing for us to do is to pick the point for the voltage, identify that, map that out, pick the point for the inverse of the current, map that out as well. Let's talk about the vertical axis first. The least value is 0.8 and the highest value is 5. So I'm thinking 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That just does that. So this is going to be 1.00 per volt, 2.00, 3.00, 4.00, 5.00 per volt. That's the inverse of that. Now, talking about the inverse of the current, the least value is 1.667 and the highest value is 10. So I'm thinking 2, 4, 6, 8, 10. Yes, 2, 4, 6, 8, 10. 2.00, 4.00, 5.00 per ampere. Sorry, 6 in 2 units, 246, and then 8.00 per ampere, then 10.00 per ampere. So that gives us a clear sense of what we want to plot. Of course, always remember somewhere at the top right hand corner of your graph to always get your scale down there for the vertical axis, which is V raised to power minus 1 in per volt. From here to here is 2 centimeter. From here to here is 2 centimeter. So 2 centimeter to represent 2 centimeter to represent to rep that is 1.00 per volt. That's on the vertical axis, and on the horizontal axis, from here to here is 2 centimeter, from here to here is 2 centimeter, from here to here is 2 centimeter. So 2 centimeter here to represent 2 per ampere. So on my horizontal axis, which is inverse of my current in per ampere, so what I have is 2 centimeter to represent 2.00 per ampere. So that way I've been able to get my scale on the top right hand corner of my graph. Of course, when you don't try that, you're also missing out on valuable marks. So you want to ensure you maximize your score. Okay, now let's try to pick the point. When my voltage is 5, my current is 10. So when you look at it, when my voltage is 5, my current is 10. When you trace this and you trace this, they definitely meet here. They meet here. I'm going to get that out. Okay, what else do I have? When my voltage is 2.5, my current is 5. When my voltage is 2.5, 2.5 should read 2.1, 2.2, 2.3, 2.4, 2.5. For inverse of my voltage, the inverse of my current reads 5. This is 4. 1, 2, 3, 4, 5. That should be 5. In between 4 and 6. In between 4 and 6. So that should be this. This is the point. This is the point. So I'm going to get that out. 2.5, then 5. And then when my voltage is 1.667, my inverse of my current is 3.33. So what I have there for my voltage 1.667, 1.1, 0.2, 0.3, 0.4, 0.5, 0.6, in between 6 and 7, in between 1.6 and 1.7, somewhere around here. That is where I am going to have for the voltage, and 3.33. So this is 2. 1, 2, 3, 4, 5. That is 3. That's 3. 3.2, 3.4. So somewhere in between this. That's where you're going to have that. Somewhere in between here, 2 and 4. So if I try to trace that out, I'm looking at, okay, I'm gonna go, yes, boom. I have it somewhere here. This is the point. So I'm gonna get that out. So that's the point for that. And then for the fourth reading, when my voltage is 1.25, of course 1.25 is going to be 1.1, 1.2. 1.25 is definitely here. 1.25 is definitely here. And my current is 2.5 at that time. So this is 2. 2.2, 2.4. 2.5 is somewhere here. You can always trace that out with your marker, not to put all those points when you are writing your exam. Okay, I'm going to trace that up. And boom, somewhere here. So I'm going to take note of that as well. Okay, let me get that clearly. A minute. I think I need to get another marker somewhere here, and that's that. So for the next one is when my voltage is 1, my current is 2. Voltage is 1, current is 2. Meet somewhere here. That's very feasible to see, and that is here, somewhere here. So we can see that point. And lastly, when the voltage is 0.83, current is 1.667, voltage is 0.83, 0.1, you see that, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So that's in between 0.8 and 0.9, just before 1, and then 1.667 for the current. 1.667, definitely this is 24681. That's 0.2, 0.4, 0.6, 0.8, then 1, 1.2, 1.4, 1.6, just before 7, somewhere here. If I trace that out, that is going to give me, that's going to give me somewhere here, somewhere here. That's the point. So I'm going to get that point out as well. Let me make it a bit more colorful. So those are my 6 points. So that's for plotting the graph. And then on question Roman figure 5, I was told to determine the slope S of the graph. That's for question 5. For question 5, I was told to determine the slope of the graph. In trying to determine the slope of this graph, I will try to take points together, as many points as I can. Okay. In fact, I was able to get the 6 points all together. I was able to get that all together, and it looks more like a line passing through the axis. Let me get that in. Looks like a straight line through the axis. I could extend it if I want. So boom, this is what I have. So I've been able to get that straight line. Then I can decide exactly what I want for my slope. I want my slope to be, but I like to make it big. So for my slope, of course, I'm already thinking of where I want to stop that. And then for the horizontal side, I just want something decent. Boom. So there you have it. So this is going to be my change, delta, change in voltage, inverse of the volts, and this is going to be my change in the inverse of the current in per ampere. So I haven't done that. I'm going to try to pick out those points. This is here. This falls on 4, and this falls on, we stopped at 10, this falls on 12. So we could go, so we already know what our horizontal axis is going to look like. Now let's pick for the vertical axis. We have it somewhere around here. You see that that's on 2, and then we have it somewhere around here. If I'm to pick that out, this is what I'm going to have with my extrapolated line, telling the examiner how I got the figures I'm going to use for my slope. So if this is 5, 4, 5, then this will be 6.00. So therefore, this is going to represent my slope. So my slope normally is always y2 minus y1 divided by x2 minus x1. But in this case, we're looking at the change in the inverse of the voltage in per volt divided by change in inverse of the current in per ampere. So when you look at this, this is going to mean, okay, I have 6 as my y2, 6.00, take out 2.00, and that's going to be in per volt divided by, in amperes, sorry, for the inverse of the current, I'm looking at 4 and 12. So I'm looking at 12.00, take out 4.00 in per ampere. So this is going to mean 6 take away 2, that's 4.00 per volt, divided by 8.00 per ampere. So this means 0.5, but of course this means 1 over V times ampere over 1 times ampere over 1. So this means 0.5 ampere per volt. That is what my slope is. Now, you recall Ohm's law. From Ohm's law, we have that V equals to IR, if you recall. So if I'm trying to make the resistance the subject, my resistance is actually voltage divided by current. This is in volts, this is in ampere. So which means when I have volts per ampere, that talks about my resistance. But in this case, it is the reverse that I have. I am having volts per ampere for ohms here. I'm having amperes per volt, which means this had gone up, then the voltage had come down. So what it means is that I can put this as well as 0.5. This is the symbol for your ohms, per ohms, and I am going to be correct, as 0.5 per ohms is the same thing as saying 0.5 ampere per volt. It's just about computing the right unit. So that ends question 5. We have 0.5 for the slope. Now let's move to question 6. So for the next question displaying on your screen is question 6. I haven't gotten our value for the slope. So for question 6, it says determine the current I. Determine I when V is 8 volt. Of course, on our graph, we didn't deal with volt. We dealt with inverse of the voltage and inverse of the current. So how do we go about this? The first thing is to get the inverse of this. So 1 over V here, that's going to be 1 over 8. And that's 0.125 volts. So we will now check the graph. From graph, we're going to trace out 0.125 per volt. 0.125 per volt. 0.125 per volt. If I am to check that, this is 0.1 and then this is 0.2 on my graph. But I need 0.125. 0.125 should be somewhere here. Look at it very well again. In the question, we were told if our voltage is 8 volts, we should, on the graph, we should determine the value of I when voltage is 8 volts. Now, we did not deal with volt from the graph. What we dealt with is inverse of the voltage. So we had calculated inverse of that voltage, V raised to power minus 1, or 1 over V, as 0.125 volts. So 0.125 volts is what we're going to try to trace out to know the corresponding figure on the inverse of the current axis. So 0.125 is somewhere here. I'm going to trace that out. So this here is 2. So 0.2, 0.3. What I have there is looking 0. Okay, 0. This is 0.125. 0.125. So this is looking 0.25. This is looking 0.25. So from my graph, inverse of my current is giving me 0.25 per ampere. So I will now have to take this to mean to current, because what I was told to look for is to determine I. Now 0.25, for me to convert this to current, that would mean 0.25 per amperes. That would mean 1 divided by 0.25. 1 divided by 0.25, that is 4.0 amperes. So that is what that means. So if I am to determine what my current will be when my voltage is 8 volts, then my current is going to be 4 amperes. Then for Roman figure 2, 16 volts, we're going to follow the same sequence. V raised to power minus 1 for 1 over 16 volts. 1 over 16 volts, if I try to compute that, that means 0.0625 per volt. Yes, that is it. Then I have to trace that out. 0.0625 0.0625 on the graph. If I'm to trace this at 0.0, not even up to 0.1, if I'm to trace that out on the, like, based on what I have on my graph, that is going to mean 0.125 amperes. If you trace it out on a paper graph, that's going to mean, if you see from graph, that's going to mean 0. From graph, you have 0.0625. From your graph, you're going to have 0.125 amperes. So for you to get the current, that will now be 1 divided by 0.125 per amperes, and that's, of course, the ampere will go up. 1 divided by 0.125, that should give you about 8 amperes, 8.0 amperes. You must have noticed the pattern. If 8 volts is giving me 4 amperes, then 16 volts is going to give me 8 amperes. Recall that from our Ohm's law, the voltage is more or less directly proportional to I. So if 8 volt had increased to 16 volt, if it had doubled, then the current also is going to double, because it's a direct proportion. Okay, that is the end of that about that. So to the next question, which is question VII. Yeah, question 7 now. Question 7 states, as you can see on your screen, question 7 says, determine the frequency F of the AC source of the alternating current from the formula F equals to, from the formula 2, from the formula from the formula X divided by 2 pi C. We're told to take pi as 22/7, and we're told to take the capacitor as 1.59 microfarad. 1.59 microfarad. Of course, take note of the unit there. So this X here, what I was told to look for the frequency, which is definitely going to be in hertz. So let's slot in the right figure. F equals to, my slope, recall, is 0.5 divided by 2 times 22. Of course, the 7, 22/7, the 7 is bound to go up, times. Now for me to convert this, this is going to be 1.59 times 10 raised to power minus 6. That way it becomes farad. Okay, so what I'm going to have here is 1.59 times 10 raised to power minus 6. I've been able to convert that from microfarad to farad. Okay, so this 7 is going to go up. So what I'm going to have is 0.5 all divided times 7 divided by 2 times 22 times 1.59 times 10 raised to power minus 6. Therefore, my frequency, if I try to compute that from my calculator, what I'm going to have is, mind you, this 10 raised to power minus 6, because it's a denominator, should now be going up as 10 raised to power 6. If you're very conversant with indices, you should know that this is now going to move up, and of course it's going to become a plus. So what we then have here is, if you compute all this figure, what you have is 5 times 10 raised to power 4 hertz. Your frequency is always in hertz. So that is going to give you 5 times 10 raised to power 4 hertz. Look at it very well. 0.5 times 7. Then what you then do is divided by 2, divided by 22, and divided by 1.59. Then you have your 10 raised to power 6 there. Of course, what you're going to have is 5 times 10 raised to power 4. So to the next question, question 8. So that ends question 7. So for question 8, we were asked, as you can see on your screen, we were told to state 2 precautions you would take to obtain accurate result if you were performing this experiment in the laboratory. If I were performing this experiment, as you can see in the circuit, AC circuit diagram, the first thing is to ensure tight connections for your wires, and also ensure clean terminals. You ensure tight connections, and then you ensure clean terminals. Okay, another thing to avoid, which I've always said, whenever you're looking at your physics practical, where you have to take your reading, of course you have to always avoid parallax error. You want to measure head on. You want to look vertically at what you're measuring, not from the side, so that it doesn't affect your precision and you don't judge the figures wrongly. Okay, so you avoid parallax error. What are we reading in this experiment? We're reading the ammeter, and we are reading on the voltmeter. That is for question VII, question 8. Also, we have for question B. Also, we have for question B. That's the end of question A at Roman figure 8. So for question B, we were asked, given another question, we were told to give a reason why a moving coil ammeter, may not be suitable for measuring current in this experiment. We are to give a reason why a moving coil ammeter may not be suitable for measuring current in this experiment. Recall that at the starts we have a capacitor and an ammeter with variable low voltage AC supply. So in this question B, why is it that a moving coil ammeter is not going to be suitable for measuring in this experiment? And it's very simple. The circuit we are dealing with is an alternating current, is an AC circuit. But what a moving coil ammeter does is quite different from AC. It doesn't measure your AC. You can see a moving coil ammeter cannot be used as it measures direct current. It's in a very simple way. A moving coil ammeter measures direct current. But in this experiment, we are talking about an alternating current. So that is the reason why a moving coil ammeter cannot be used. Also, we were told to suggest one type of ammeter that could be used. One type of ammeter that can be used for this experiment is a moving iron, not a moving coil. Moving iron instrument can be used to measure alternating current. So that is B1. Then for B2, we're told to define capacitive reactance. You can see that on your screen. Capacitive reactance. And we were told to write down an expression for the reactance of the circuit used for this experiment. Now, capacitive reactance XC is the opposition to the flow of the alternating current by the capacitor. Think about it. Capacitive reactance. It offers opposition to the flow of the alternating current, but this time by the capacitor. That is why we call it capacitive reactance. Okay, the second part of this Roman figure 2, we were told to write down an expression for the reactance. We were told to write down an expression for the reactance. Okay, so in this case, my capacitive reactance, if you look at it very well, is inverse of my slope. Take note that on question 7, we were given an expression f, frequency equals to the slope divided by 2 pi c, the capacitance. So if you're telling me now to look for the to write an expression for the capacitive reactance, for my capacitive reactance, that is 1 over the slope. Now, trying to make the slope the subject here, my slope is actually 2 pi fc, because this is going to move to this side. Of course, this is moving here, this is moving here. So my capacitive reactance based on this experiment is actually xc equals to, the slope is 1 divided by 2 pi fc in place of the x. So this is an expression for the reactance in this circuit that we have, and that just ends the question. Thank you. Do remember to subscribe, turn on the notification bell, comment, and as well like our videos. You can always tell us what you feel about those this alternative to practical questions in the comment section. Also, do well to visit 300plusacademy.com, where you can link up with various scholars like you preparing for the same exam, and you can always, of course, let us know your view. Thank you. I'm out.